This video will explain how to represent bivariate data using a scatterplot and line of best fit. I suspect this is part 1 of 2 parts video. So bivariate data. Bivariate data means 2 variables. So we're looking at data that has 2 bits of information recorded about it. Let's look at this graph first. We can see here that we've got number of visitors at a beach and we've got daily temperature in Fahrenheit. So the information that's been recorded is for which days, temperatures, how many visitors they get to a beach. This one over here, one close to my heart, study time in minutes compared to results in a quiz, for example. So bivariate data means 2 sets of related data, so something that's have some sort of relationship to each other. The graphs are the data is graphed on what's called a scatterplot, which is ones you saw the picture on the previous screen, and we're going to draw a line of best fit to model the relationship between the variables, and that relationship is called correlation. And we're going to look at that as well. Let's look at some data. Seem to be a little bit cut off at the top here. There we go. So we've got some data here, and the data, and I've messed that up. The data is Year 10 maths results, actually, compared to the same students, and these are the students down here, their Maths B results. Now, Maths B in Queensland is a more difficult level of maths than other maths. So we're looking at how students did in their Year 10 studies and compared it to how they then did in their Year 11 studies. Now, common sense seems to tell us that the better you do in Year 10 maths, the better you'll do in Year 11 maths, and we're hoping that that's what our graph is going to show us. So first of all, we need to set up our axes. And in order to do that, we need to determine which of our variables is dependent and which is independent. Now, if you're not really sure, what I suggest that you do is you put the 2 variables into the sentence with the words depends on in between. So, for example, our 2 variables are Year 10 results and Year 11 results. So we're going to say, do Year 10 results depend on Year 11 results? Or do Year 11 results depend on Year 10 results? I think the latter makes more sense. Sometimes in scatterplots you won't have a dependent and an independent, you just make your own call. So our dependent variable is going to go on the y-axis or the vertical axis, and the independent is going to go on the x-axis or the horizontal axis. So that's what I've done here. The independent results, the results that don't depend on anything, are the Year 10 results, and the Maths B Year 11 results are going to go on the vertical. They depend on the Year 10 results. So this vertical axis depends on the variable on the horizontal axis. So now we need to choose an appropriate scale. Scatterplots rarely start at 0, 0. You want to only really have the numbers that are in your data represented. You don't want any great big sections of your graph to be blank. So what I've done here is I've gone through the Year 10 results and I've circled the smallest number and the largest number, and I've done the same thing with the Year 11 results. So I know that my data, that's incorrect there, I must have moved this. There we go, that's better. 28 and 47. So I know that my lowest number on my horizontal axis has to be 28, and my highest one has to go at least to 47. So I set up my axes. These little squiggly lines I've got in the corner here indicate to us that we've squashed up all of the part of the number line lower than 28. Between 0 and 28 has been squeezed up, sort of like concertina style, and that's what that little wiggly line represents. You'll see that there was one on the previous page as well. Where are we? Here, there's a little wiggly line. This scale here started at 0 because each of these sections is 75, but this one down here didn't start at 0, so it's got a little squiggly line there to represent that. So starting at 28, I set up my axes the way that I want them to do. I don't let the scale determine how long my axes are going to be. I determine how long they're going to be to start with. And then I start counting. I put my lowest number there, and I usually start with ones, and I go 28, 29, 30, 31, 32, 33, 34. And I'm never going to get to 47 by the time I get down to this arrow. Let's try twos, 28, 30, 32, 34, 36, 38, 40, 42, 44. I'm not going to get to 47 in that space. So I didn't have any alternative but to count in threes. So 28, 31, 34, 37, 40, 43, 46, 49. Doesn't quite reach the end, but it's the best of the options that I had. And I do the same thing here. Now, coincidentally, I'm also counting up in threes for this axis, but you can be counting in fours or fives or twos or ones or tens. It doesn't really matter. Whatever makes your scale fit. So we did that by identifying the smallest number and the largest number and then fitting the scale. Now when you do your own question, you might very well have a completely different scale. You might have a different scale to even the person sitting next to you. Another thing that you need to think about, and I didn't think about this when I was doing this graph, is that usually you have questions to be answered about this data. If the question answered talks about, someone who's coming into the class with Year 10 results of 60%, then I'm not going to be able to answer that question because 60 doesn't appear on my graph. So just be a little bit aware of that. Sometimes your scale needs to go beyond the data that you've been given so that you can make predictions beyond the data. So check the questions that need to be answered. Is there a question that asks you to extrapolate? I'll talk about that word later. Beyond the data you have. In that case, make sure your axes allow you to answer those questions. Okay, so I started plotting the points. Every single pair of points gets a little cross. So 32, 27 is 32 along the x-axis, and 27, and that's that little cross there. Now I've done all of them except for the last three. The last three are 33, 31. Let's grab 33, 31. 33, 31 is there. And 34, 29. Start at 34 and go up to 29. And this one here, 28 down here. And 22, so about there. And there I have a lovely, lovely scattered plot of crosses, and not surprisingly they seem to be going upwards from left to right, which sort of matches what you would expect, that the bigger the Year 10 results, the bigger the Year 11 results. We would expect people who didn't do very well in Year 10 to not do very well in Year 11. We expect people who did very well in Year 10 to do very well in Year 11. And so what we're going to do now is we're going to do a line of best fit. Now a line of best fit is just a line that's going to run through all of these crosses that we're going to from then on use as a representation of the relationship between those two variables. In order to do the line of best fit, we need one more little cross. And that one more little cross I usually do in a different color, and I put a circle around it. Now that one more little cross is going to help us draw our line of best fit. And the way we get that one more little cross is we get it from taking the mean of each of the sets of variables. So the mean, as you know, is the meanest. Means you add them all up and divide by how many scores that are there. Now I have added them all up, all the Year 10 results up, and I got 407. Divide by 14 to make the mean or average, and I get 36.2. The sum of all of the Year 11 results was 437. Divide by 14 gives me 31.2. So I'm graphing these 2 points, 36.2, 31.2. I'm making it a different color and I'm putting a circle around it. And that's actually our pivot point for our line of best fit. There are several methods for doing the line of best fit, but the method that I'm going to show in this video is my video, so I can do it the way I like to do it. So we've found the mean of both sets and we've plotted those 2 on the graph, and we've circled it. Now we need to place the ruler on that point and, following the general pattern of the crosses, draw a line that has half the crosses above the line and half below. The 2-point method for finding the equation of a line, we'll cover that in another video, and that's mainly for the higher maths levels. So I have done my line of best fit. Let me just get a ruler out here. Where is the ruler? There is our ruler. And I'm just going to try and demonstrate to you how we go about wiggling this line into the right place, because it does look like I've just miraculously done it. Let me just pause the video, and I'm going to wiggle the ruler. So I've just plonked the ruler down in this spot, and this line that I've just got the ruler sitting at is wrong, but a lot of people will think it's right because it fits 2 of the 3 requirements for the line of best fit. It goes through the little red cross, and there are 1, 2, 3, 4, 5, 6, 7 crosses above the line, and there are 1, 2, 3, 4, 5, 6, 7 crosses below the line. But it doesn't follow the pattern of the crosses, and that's the one that most people overlook. It's the most important one. Your line of best fit has to be representative of the pattern of the crosses. So it needs to follow the pattern of the crosses. So I'm going to pause again and wiggle it a little bit more. Now, where I've placed the ruler this time, it's not bad. It is certainly following the pattern of the crosses better than the previous one. It's going through the red cross. It's got 1, 2, 3, 4. If you count the 2 that are on the line, there's 7 above, and I suspect that there are 7 below. But I still don't think it's as best that you can be. But it is an imprecise method. So you could very well find that your answer is slightly different to the person beside you. But I think that mine, the one that I've got there originally, I think it's the best. So there's our line of best fit. Let's look at what that actually says in terms of the word correlation about our set of data. Now, our set of data is definitely sloping upwards from left to right, and just like the word gradient, sloping upwards from left to right means positive correlation. There's a positive relationship between Year 10 results and Year 11 results, and a positive relationship means as one increases, the other increases. A negative relationship means as one increases, the other decreases, and it would look like a downward sloping line. An example of something that would have a negative correlation might be, let me think, the number of hours you spend exercising a week and your resting heart rate. Now, the fitter you are, the lower your heart rate. You lower your resting heart rate. So as you spend more time exercising, then your heart rate should come down. So that would be an example of negative correlation. Now, our crosses are also really quite close into the line of best fit. They're not scattered all over the place. So that's called a strong correlation, strong positive correlation. So this example here just shows you positive correlation going upwards from left to right, and even that is not as good as our example, but it's certainly a strong positive correlation. This one is an example of a negative correlation, and it's even stronger, even though those crosses are all cluttered around their line of best fit. And this one here, no correlation. It's just like someone has taken a paint gun and scattered the board. So the line of best fit allows us to get some more information than what we had already gathered. So the 2 words that you need to be able to know about those is interpolate or interpolation, and extrapolate or extrapolation. Interpolate means to predict values between given values in a set of data, usually using the line of best fit. So what do we mean by in between given values? Let's go back to our thing here. Here, we don't have every single value from 28 to 47. For example, we've got a 29, we don't have a 30. So we don't really know from our gathered data what year 11 results we would expect from someone who would have got 30 in their year 10 results, because we don't have it in our gathered data. But we now have a line of best fit which seems to represent the relationship, so we can make a prediction about that. So here's 30 in the year 10 results. We could pop up to our line of best fit. When we meet the line of best fit, we'd pop across to here, and we would see that we would expect that the year 11 student who got 30 in year 10 would get 24 in year 11. Now, it's an approximation. Our line of best fit is an approximation, but it's a good approximation. The strength of the correlation is strong, so we would expect it to be quite accurate. Let's actually do that. Oh, and extrapolate means predict beyond the given values. So this is where I didn't prepare very well. If I wanted to know the year 11 results of someone who got 55% in year 10, up here somewhere, unfortunately I haven't given myself enough graph to make that prediction. But if I'd thought ahead of time that maybe that question might be asked, then I could have extended my scale and I could have extended my line of best fit and answered that question. Okay, so let's look at this little example of interpolation before this video finishes. What year 11 result would you predict of a student who got 46% in year 10? So let's go through it. We need a line. Year 10 results of 46, so here's 46 here, so we're going to go straight up to our line of best fit, and as soon as we get there we're going to stop, and then we're going to go straight across, and we're going to read that to be 42, 43, 44, 44 or 43 point something, approximately 44% we would expect them to get in their year 11 results based on our line of best fit. But once again, your line of best fit might be slightly different to the person beside you, so you might have slightly different answers, but you know, they shouldn't be more than 1 or 2 away from each other. I hope this has been clear for you. Watch my other videos.